If we were to name the figure who forced open the door to the quantum world, it would be Max Planck. In 1900, grappling with the intractable problem of black-body radiation, a phenomenon classical physics could not explain, Planck found himself backed into a theoretical corner. Out of sheer necessity, he made a radical, intuition-defying assumption: energy is not emitted or absorbed continuously, but in discrete packets. He called these packets quanta. The energy of each quantum, he proposed, was equal to a constant later named the Planck constant multiplied by the frequency of the radiation. This hypothesis was a key, cautiously tapping on the door to a new world. But even Planck himself didn't anticipate that this conceptual fix, born of desperation, would utterly humanity's understanding of reality. Perhaps too deeply entrenched in classical thought, Planck spent years afterward trying to reconcile the quantum back into a classical framework, like peeking through the door, but never fully stepping through. The one who forcefully shoved the door wide open was the scientific giant, Albert Einstein. In his miracle year of 1905, while explaining the photoelectric effect, Einstein boldly adopted Planck's quantum idea. He proposed that light could behave not only as a wave, but also as a stream of particle-like packets called light quanta, later termed photons, each carrying energy according to Planck's formula. This concept of wave-particle duality shattered the classical absolute distinction between waves and particles, ripping the quantum door open for good. Following this, a generation of young physicists, unafraid to challenge tradition, rushed to explore the microscopic quantum realm. But, to understand their breakthroughs, we must first set the stage, the pre-quantum stage, a world of atoms and mysteries. Even before 1900, physicists had some basic understanding of the microscopic world. The idea that atoms were the fundamental, indivisible building blocks of matter was widely accepted. Dmitri Mendeleev, with remarkable insight, had even created the periodic table based on atomic weights, accurately predicting elements like gallium and germanium before their discovery. But science relies on evidence, not just philosophy. The first experimental evidence that atoms were not indivisible came from Marie Curie. Around 1896, she discovered radioactivity. Uranium atoms spontaneously emitted invisible rays. This was crucial because radioactivity is an internal atomic process, unrelated to chemical reactions. It demonstrated that one type of atom could transmute into another, proving atoms had internal structure. The first subatomic particle to be identified was the electron, discovered by J.J. Thomson in 1897. Through ingenious experiments with cathode rays, he showed they were composed of negatively charged particles much lighter than the smallest atom, hydrogen. He concluded these particles were universal constituents of all atoms. This discovery led Thomson to propose his plum pudding model of the atom, a diffuse, positively charged pudding with negatively charged electrons embedded within like plums, resulting in a neutral atom. It seemed plausible, but was soon to be spectacularly overturned by one of his own students. Rutherford's nuclear atom, a shot heard round the world. Ernest Rutherford, a brilliant experimentalist, had already made his name in radioactivity, correctly identifying that it involved particles like alpha particles being ejected from atoms. His work was so foundational, he was awarded the Nobel Prize in Chemistry in 1908, a fact he reportedly found amusing, famously quipping, "All science is either physics or stamp collecting." His expertise with alpha particles proved pivotal. He realized these high-energy, positively charged particles could be used as probes to investigate the atom's interior. In the famous gold-full experiment, 1911, his team fired a beam of alpha particles at a thin sheet of gold foil. According to the plum pudding model, most particles should pass through with minimal deflection. The results were astounding. While most particles did pass straight through, A small number were deflected at large angles, and a very few bounced directly backward. Rutherford recalled his astonishment. It was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it came back and hit you. This could only mean one thing. The atom was mostly empty space, with its positive charge and nearly all its mass concentrated in an incredibly tiny, dense core, the atomic nucleus. Electrons must orbit this nucleus at a great distance. This was the birth of the nuclear model of the atom, the fatal flaw in Bohr's quantum leap. While Rutherford's model fit the scattering data, it created a monumental problem for classical physics: atomic stability. According to Maxwell's laws, an orbiting electron is an accelerating charge and must continuously radiate energy. It would spiral into the nucleus in a fraction of a second, causing the atom to collapse. Yet, atoms are perfectly stable. The solution came from a young Danish theorist, Niels Bohr, who joined Rutherford's lab in Manchester. Bohr made a radical leap, importing the quantum idea into atomic structure. In 1913, he proposed a new model with two revolutionary postulates: quantized orbits. Electrons can only exist in specific, discrete, stable orbits around the nucleus. They do not radiate energy, all in these orbits, defying classical electrodynamics. Quantum jumps. Electrons can only jump between these fixed orbits. When jumping to a lower energy orbit, they emit a photon whose energy equals the difference between the orbits E equals h nu. Absorbing a photon of the same energy causes a jump to a higher orbit. This model directly solved the stability problem, but it was initially seen as a strange, ad hoc mixture of classical and quantum rules. Its salvation came from an unexpected place: atomic spectra. A colleague pointed Bohr to the Bohr formula, an empirical equation had accurately described the wavelengths of light emitted by hydrogen atoms. No one knew why it worked. To his delight, Bohr found that his model could derive the Bohr formula from first principles. The constants in the formula were directly related to fundamental constants like Planck's constant and the electron's charge and mass. Furthermore, Bohr's model predicted new spectral lines in hydrogen, which were soon confirmed experimentally. This was a triumph. Bohr's model was no longer just a curious idea. It had predictive power. It marked the first successful application of quantum theory to the structure of matter, becoming a cornerstone of the new quantum mechanics. The inevitable generational shift. Bohr's theory was a breakthrough, but it was incomplete. It couldn't explain multi-electron atoms, and the quantum jump remained mysterious. Even Einstein was uneasy, questioning the seemingly magical, causal nature of the jumps. Yet, it was the younger generation unburdened by classical dogma who embraced this new path. As Planck himself somberly noted, a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. Bohr's model served as a crucial bridge. It paved the way for the more complete and profound theories developed by Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, ultimately leading to the full-fledged quantum theory that defines our modern understanding of the atomic world.